Okay, welcome to the class. Today we're going to have a look at the second topic of chapter 5, calorimetry and enthalpy. Firefighters risk their lives every day when they enter burning buildings. To help reduce this risk, they wear suits that protect them from the high temperatures of fire, which is illustrated in figure 1 here. The temperature inside the protective suit remains in a range that allows the firefighter to continue working. The heat-resistant fibers used to construct these suits protect firefighters from high temperatures while still allowing them to move. Most protective clothing worn by firefighters is constructed with a fabric called Nomex. When Nomex is exposed to high temperatures, the fibers absorb thermal energy and swell, which prevents the firefighter's skin from increasing in temperature and burning. Obviously, fibers such as the cotton in a t-shirt cannot absorb enough thermal energy to protect a person from fire. So what chemical property describes the ability of a substance to absorb thermal energy? Okay, so consider this scenario here. Have you ever dashed across hot beach sand and then you could stand comfortably in the cool water? Both the water and the sand are heated by the same energy source, the sun, and yet the sand feels so much hotter. Both substances have been heated by the sun for the same amount of time, so why is the temperature of the sand so much higher? This difference in temperature is caused by a difference in the specific heat capacity of water and sand. The term specific heat capacity, which is usually denoted in letter C, is the quantity of thermal energy required to raise the temperature of 1 gram of substances by 1 degree Celsius. The SI units for specific heat capacity are joules per gram temperature in Celsius. It takes a lot of thermal energy to rise the temperature of a substance with a high specific heat capacity, such as water, but relatively little to raise the temperature of a substance with low specific heat capacity, such as sand. So have a look at table 1 here, which shows specific heat capacities of some common substances. Note that water's specific heat capacity is more than 5 times that of sand. This means that the amount of thermal energy required to raise the temperature of water by 1 degree Celsius is 5 times the amount of thermal energy required to raise the temperature of sand. The high specific heat capacity of water is the reason the temperature of a lake remains cool well into the summer, while the surrounding land is warm. Substances with higher specific heat capacity also take longer to cool. A lake, for example, remains warm into autumn, long after the land temperature has decreased. It will also remain cool in the spring longer than the surrounding land. Okay, next let's have a look at the concept of calorimetry and thermal energy transfer. Heating water on a gas stove transfers thermal energy from the natural gas to the water. This energy transfer increases the kinetic energy of the water molecules, which makes them move faster. As a result, the average kinetic energy or temperature of the water increases. One way that scientists can study thermal energy transfers is by calorimetry. Calorimetry is a process of measuring energy changes during a physical or chemical change. A calorimeter A calorimeter is a device used to measure energy changes during a physical or chemical change. The design of calorimeters varies. So you can see figure 2 shows 3 examples of calorimeters. In general, a calorimeter consists of a well-insulated reaction chamber, a tight-fitting cover with insulated holes for a thermometer, and some mechanisms to stir the calorimeter contents. Using a insulated chamber minimizes energy losses to the surroundings. A tight lid prevents matter from leaving or entering the calorimeter. Of course, a simple calorimeter can be made from 2 nested polystyrene foam cups and a lid to hold a stirrer and thermometer, as shown here in figure 2a. The inner cup is where the chemical system being studied. For example, a chemical reaction is placed. The inner cup also holds a liquid, usually water. Any change in thermal energy of the system is detected at the temperature change of the water. The outer cup provides additional insulation. If you have ever kept a hot or cold liquid in a foam cup for a long time, you know that thermal energy eventually escapes. That is why more elaborate calorimeters are used, such as the model shown here in figure 2b, when precise measurements are required. Reactions carried out in calorimeters, like those in figure 2a or 2b, take place under constant pressure, since a small amount of gas will always escape. As a result, the volume of the contents will change, which keeps the pressure constant. Therefore, to study the physical or chemical change involving a gas or gases, chemists use a bomb calorimeter, which is shown here in figure 2c. A bomb calorimeter is a very rigid, tightly sealed vessel that prevents almost all gas from escaping while maintaining a constant volume. If a physical or chemical change produces gas or gases, the pressure in the bomb calorimeter will increase. If the change consumes gas or gases, the pressure will decrease. A bomb calorimeter is particularly useful for studying the energy changes of combustion reactions, since one reactant is always oxygen gas, and the products always include one or more gases. Okay, next let's have a look at how we can calculate calorimetry. For the investigations provided in this lesson, we will use a coffee cup calorimeter. When analyzing data obtained using a coffee cup calorimeter shown here, usually we'll make the following assumptions first. First, any thermal energy transferred from the calorimeter to the outside environment is negligible. Second, any thermal energy absorbed by the calorimeter itself is negligible. Third, all dilute aqueous solutions have the same density, which is assumed to be 1 gram per milliliter, and specific heat capacity as water, which is 4.18 joules per gram degrees Celsius. So you need to memorize this specific constant. That's the specific heat capacity for water. Okay, please write this down on your notebook. These assumptions are valid only for physical or chemical changes that take place in water or dilute aqueous solution. In calorimetry, the total amount of thermal energy absorbed or released by a chemical system is given the symbol lowercase q. The magnitude of Q depends on 3 factors, which are: first, the mass of the substances; second, the specific heat capacity of the substance; and third, the temperature change experienced by the substance as it warms or cools. And the value of Q is calculated using the equation shown here on the top left. Q equals mc delta T, where m is the mass of the substances, C is the specific heat capacity of the substance, and delta T is the change in temperature of that substance. The change in temperature is the difference between the final temperature, T final, and the initial temperature, T initial, which can be written as the formula in the middle. Delta T equals T final subtracted by T initial. The value of lowercase q has two parts. The magnitude of q tells us how much energy is involved, and the sign tells us the direction of the energy transfer. The transfer of energy from a system to the surroundings in a coffee cup calorimetry is illustrated here in figure 3. The system is composed only of the components of the physical or chemical change that occurs. The water in the coffee cup calorimeter is the surroundings, and all energy transfers are assumed to take place between the system and the water. The calorimeter itself is assumed not to be involved in these energy transfers. We can use the value of Q for the surroundings, namely the water, to predict whether a change will be exothermic or endothermic. That is, if Q has negative value, the system transfers thermal energy to the surroundings, and the change is then exothermic. The temperature of the water or the surroundings in the calorimeter increases. If Q has a positive value, then the system absorbs thermal energy from its surroundings, and the change is endothermic. The temperature of the water in the calorimeter decreases. Since energy cannot be destroyed, the total thermal energy of the system and the surroundings remain constant. Therefore, the sum of Q system plus Q surroundings should equal 0, right? Since these symbols represent equal quantities but with opposite signs, which is shown here on the right side, Q system plus Q surroundings always equals 0, or you could also say Q system equals negative Q surroundings. Okay, so this is a concept of how we can calculate the calorimetry of a reaction. So next, let's have a look at a sample problem to illustrate the concept in concrete. So consider this sample problem here. A student places 50.0 milliliters of liquid water at 21 degrees Celsius into a coffee cup calorimeter. She places a sample of gold at 100 degrees Celsius into the calorimeter. The final temperature of the water is 21.33 degrees Celsius. The specific heat capacity of water is given to you, which is a constant you need to remember. And the density of water, D, is also a constant number you should remember, 1 gram per milliliter. Calculate the quantity of thermal energy Q absorbed by the water in the calorimeter. Okay, I'll give you some time to consider this question by yourself, and then we'll have a look at the solution together, okay? Okay, let's have a look at the solution together. So given this information, first we can determine the mass of the water, M, in the calorimeter, right? M equals Vd, which is 50 grams. Then we can determine the change in temperature, delta T, of the water in the calorimeter. And that is 21.33 degrees Celsius subtracted by 21 degrees Celsius, which gives us 0.33 degrees Celsius. And then in the next step, we can calculate the quantity of thermal energy Q transferred to the water in the calorimeter, where Q equals mc delta T. So put these numbers in, we know Q equals 69 joules. Then check that sign of Q makes sense. Since the temperature in the water increases, water absorbs energy, therefore Q should be positive. Then the final statement is the quantity of thermal energy absorbed by the water is 69 joules. Any questions? Okay, if not, let's consider another sample problem. Problem 2 here. Using the value for Q that you calculated in the previous sample problem, calculate the specific heat capacity C of the sample of gold. If its mass is 6.77 grams, assumes that the final temperature of the gold sample was the same as the final temperature of the water in the calorimeter. Again, I'll give you some time to consider this problem by yourself, and then we'll have a look at the solution together, okay? Alright, let's have a look at the solution together. So first we could determine the change in temperature, delta T, of the gold sample, which is negative 78.67 degrees Celsius, and then determine if Q should be positive or negative. Well, we know from sample problem 1 that 69 joules of the thermal energy was absorbed by the water or the surroundings. Then the quantity of thermal energy lost by the gold sample, or namely the system, must be of the same magnitude but opposite in sign, right? Which means Q equals negative 69 joules. Then we can rearrange Q equals mc delta T to solve for C, which is 0.13 joules per gram degrees Celsius. Then the final statement is the specific heat capacity of the sample of gold is 0.13 joules per gram degrees Celsius. Any questions? Alright, if not, let's have a look at another problem here. Consider the sample problem 3. Try to solve this by yourself, and then we'll have a look at the solution together, okay? Alright, now let's have a look at the solution of this question. So we know the thermal energy of water absorbed is given by this equation here, right? Q H2O or Q water equals M H2O times C H2O times delta T. And we also know the mass of the water is 100 grams according to the given information. And the specific heat capacity of water is 4.18 joules per gram degrees Celsius. And then the temperature change of the water is 6.9 degrees Celsius. And therefore we know the heat that the water absorbs is 2,884.2 joules. In other words, thermal energy the system absorbs is given by negative of that value, negative 2884.2 joules. And therefore we can know the quantity of the thermal energy transferred by the reaction to the water is 2884.2 joules, and the reaction is exothermic. So have a look at the solution here. Any questions, just let me know, okay? Alright, next let's have a look at the concept of enthalpy change. Every substance undergoing a chemical or physical change contains a certain amount of thermal energy. The total amount of thermal energy is sometimes called enthalpy, which is denoted by the uppercase letter H. Chemists have yet to find a way to measure the enthalpy of a given substance. However, the energy change that occurs in a system during a reaction, called enthalpy change, denoted by delta H, can be measured using calorimetry data. So let's examine why this is possible. Chemists have found that as long as pressure remains constant, the enthalpy change of the chemical system is equal to the flow of thermal energy in and out of the system. Or this could be expressed as delta H of the system equals the absolute value of the lowercase q system. For a chemical reaction, the enthalpy change delta H is given by the equation. Delta H is H products minus H reactants. That is the enthalpy of the products subtracted by the enthalpy of the reactants. When the products of a reaction have a greater enthalpy than the reactants, delta H will be positive. System absorbs thermal energy from its surroundings, and the reaction is endothermic. On the other hand, if the enthalpy of the product is less than that of the reactants, delta H will be negative. In this case, the system releases thermal energy to its surroundings, and the reaction is exothermic. In a summary, if delta H is above 0, we have an endothermic reaction. Whereas if delta H is less than 0, we will have an exothermic reaction. For example, suppose we use a bond calorimeter to determine the enthalpy of the reaction in which magnesium reacts with an aqueous solution of hydrochloric acid. According to the net ionic equation shown on the top, the chemical system consists of solid magnesium, aqueous hydrochloric acid, magnesium ions, and hydrogen gas. The surroundings are the liquid water in the calorimeter. During the reaction, the water temperature increases. We can infer from the temperature increase that the energy is transferred from the chemical system to the surroundings, which is illustrated in figure 4 here. Therefore, the products have a lower enthalpy than the reactants, so we have delta H is less than 0, right? And therefore, this is an exothermic reaction. Okay, next, another important concept is called molar enthalpy change. The molar enthalpy change, which is usually denoted by delta R, of reaction for a substance is the energy change that occurs when one more of the substance undergoes a physical, chemical, or nuclear change. The SI unit for molar enthalpy change is joules per mole. In the symbol delta HR, the subscript R indicates the chemical reaction type. So you can have a look at table 2 here, which illustrates how the symbol for molar enthalpy change is written for various types of chemical reactions, and gives examples of balanced equations for each. Notice that when we write the balanced equation for the molar enthalpy change of formation of a product, the coefficient of the product must always equal 1. Other substances in the equation may have fractional coefficients as a result. The quantity of energy involved in a change depends on the quantity of matter that undergoes the change. For example, it takes twice the quantity of energy to convert 1 liter of liquid water to water vapor as it does to convert 500 milliliter to calculate a enthalpy change delta H for some amount of substances other than 1 mole, you need to obtain the molar enthalpy value, delta HR, from a reference source, and then use the formula delta H equals N times delta HR, where N is amount in moles, and delta HR is a molar enthalpy change of the reaction. So following this concept, let's have a look at a sample problem here. Calculate delta H for vaporization reactions. Ethanol, whose chemical formula is CH3CH2OH, is used to disinfect the skin prior to an ejection. If a 1 gram sample of ethanol is spread across the skin and evaporated, what is the expected enthalpy change? The molar enthalpy of vaporization of ethanol is 38.6 kilojoules per mole. Okay, I'll give you some time to consider this question by yourself, and after that we'll have a look at the solution together. Okay, you can start now. Alright, now let's have a look at the solution. So we know the molar mass of the ethanol is calculated by using this method, right? Which is given by 46.08 grams per mole. So the amount of the ethanol is given by N equals the mass of the ethanol over its molar mass, which is 1 over 46.08 moles. So we can just leave these numbers here. You don't have to use any approximation because it's just some intermediate steps. Then we know the magnitude of the enthalpy change is given by delta H vaporization multiplied by the quantity of the ethanol N. And put all these numbers in, we have 38.6 kilojoules per mole times 1 over 46.08 moles, and this will give us approximately 8.26 times 10 to the power of -1 kilojoules. And therefore we know this is actually a endothermic reaction because we have delta H is above 0, right? And enthalpy change is given by this number here, positive 8.26 times 10 to the power of -1 kilojoules. Any questions? Okay, if not, let's consider another sample problem. So I'm not gonna read all of these for you, so please have a look at this question by yourself and try to solve it in your own words, okay? And after that, we'll have a look at the solution together. Alright, now let's have a look at the solution together. Okay, first of all, we can calculate the thermal energy the water releases, which is mass of the water times the specific heat capacity of the water times the temperature change of the water, right? Which gives us 19.75 joules. Then the enthalpy change for this dissolution reaction is the same number here, 19.75 joules, which is positive for endothermic reaction. We also know the molar mass of the substance, potassium bromide, is 39.1 plus 79.9, which gives us 119 grams per mole. So the amount of the substance, potassium bromide, is given by the mass over the molar mass of these substances, which is 0.08824 moles. And last, we can calculate the molar enthalpy change, which is delta H over the amount of the potassium bromide here, and that is 19.75 joules over 0.08824 moles, which is 18.356 kilojoules per mole. Did you get it? Okay. If you don't have any questions, let's have a look at a next topic, representing molar enthalpy changes. All chemical reactions undergo a change in enthalpy. Spectacular reactions such as the combustion of highly flammable liquid ethanol are obviously exothermic. In most chemical reactions, however, the enthalpy change is more subtle. In fact, it is often difficult to tell whether a reaction is exothermic or endothermic. Therefore, it's important to have a clear way of communicating this information in the chemical equation for the reaction. A chemical equation that describes the enthalpy change of a reaction is called a thermochemical equation. For example, the synthesis of water from its elements is an exothermic reaction and can be represented by the two thermochemical equations, as shown here on top left. In the first thermochemical equation, an energy term is on the product side to indicate that the energy is released by the chemical system. In the second thermochemical equation, the enthalpy change delta H is written after the balanced chemical equation. In this example, the enthalpy change is negative, indicating that the process is exothermic. Notice that both equations indicate that 1 mole of hydrogen reacts to release 285 kilojoules of thermal energy. The only difference is how this energy change is communicated. And now consider the reverse of this synthesis reaction. Electricity can be used to decompose water into its elements. For this reaction to occur, water must absorb 285 kilojoules per mole of energy. This reaction can be represented by the following two thermochemical equations, which is illustrated on the bottom. So in the first equation, the energy term is on the reactant side, indicating that energy is absorbed by the system. In the second equation, the molar enthalpy term has a positive sign, indicating that decomposition reaction is endothermic. Again, you could use either one of them. The only difference is how this energy change is communicated. Well, we can also represent the enthalpy change of a reaction using a potential energy diagram. In a chemical reaction, both reactants and products have potential energy. In the potential energy diagram, we express the potential energy, which is y-axis, as a function of the reaction progress, which is x-axis. For an exothermic reaction, the reactants have more potential energy than the products. Therefore, we will draw the line for the potential energy of the reactants higher than the line drawn for the products, which is illustrated here in figure 6a. In an endothermic reaction, the products have more potential energy than the reactants, as the system absorbs energy, which is shown here in figure 6b. Neither of the axes have numerical values, since we are only describing the enthalpy change delta H of the reaction. So if you are clear with the concept now, let's have a look at a sample problem to check your understanding. Okay, first problem. Combustion of methane gas CH4 is an exothermic reaction. When 1 mole of methane burns, 802.3 kilojoules of energy is released. Can you write the thermochemical equation both by representing the energy change as the delta H value and by representing the energy change as the energy term in the equation? Okay, you should have finished. Let's have a look at the solution. Okay, step 1, we can write a balanced chemical equation without the energy term. Then step 2, to write the thermochemical equation with energy included. Decide whether the energy term should be on the reactant or product side. Since an exothermic reaction releases energy, we can place the energy term on the right side or product side of the equation. Also notice that in this type of reaction, in this type of equation, we do not change the sign of the thermal energy term. And then to write the thermochemical equation with the delta H notation, determine the sign of the enthalpy change. Since combustion reactions are exothermic, the enthalpy change will have a negative value, right? So if you want to express that using the delta H notation, so you need to write delta HC here equals negative 802.3 kilojoules. Can you see the difference? Okay, and next let's have a look at another problem. Can you draw potential energy diagrams for the following 3 reactions? Can you recall what is a potential energy diagram? We have just talked about this concept. Okay, I'll give you some time to solve this question by yourself, and then we'll have a look at the solution for each of them, okay? Alright, let's have a look at the result. The first one, since the energy term is on the reactant side of the equation, it's a endothermic reaction. You can draw the reaction coordinates with x-axis labeled reaction progress and the y-axis labeled potential energy, EP, in kilojoules. Since the product will have greater potential energy than the reactant, point the arrow from the reactant upward to the product. Write the reactant on the lower left-hand side of the graph and the product on the upper right-hand side of the graph. Also include delta H of the reaction. This process is sublimation. So delta H is delta H sub. The graph is shown here. For the second reaction, since delta H is negative, this reaction is exothermic. In an exothermic reaction, the reactants will have greater energy than the products. So the arrow will point downward from the reactant to the product. Okay, then last one. Since the energy term is on the side of the product, the reaction is exothermic. The equation is for the formation of 2 mole of AgCl in solid state, so we divide reactants, product, and enthalpy in half. Draw the potential energy diagram per mole of the product formed. Okay, so this is the end of today's lesson. If you don't have any question, I'll see you next time. Bye.